So welcome everyone to our Integrability Journal Club, and Andrea will present the speaker, please.
Hello, welcome everyone. So this week we are very happy to have Ines Aniceto, and also thanks to Ines for bearing with us with the change of schedule and all the changes that we made. And so she'll be telling us about new results about integrable field theories with an interacting massless vector. Please, Ines.
Okay, thank you. Well, thank you for the opportunity to chat. Also, because there's plenty of things that we do not understand in all of this. So anyone who has new ideas and new directions, it will be very welcome. So yeah, and I'm sorry about the whole schedule. Is half of the week running after a 4-year-old makes things slightly more challenging to actually change at times. So yeah, I'll be talking about basically how to include the information about massless virtual particles into the energy corrections of a massive energy state. And as of course, my interest is in ADS-CFT, but in particular, meaning we haven't yet been able to achieve that quite yet. So we were trying to actually find different theories that would allow us to have hints about how to handle this issue. So just as a start, I know this is an Integrability Journal Club, so I'll be saying nothing new in the next few slides, but in any case, let me just go through them quite quickly. So
that's not a conventional thing for the Integrability Club, right? Usually people do say new things.
So, okay, in integrable systems, we do have a very efficient, if not extremely complicated, as you mentioned, Bogdan, last time, way of calculating the energy spectrum for a system of size L, where L can be discrete, like a spin chain, or it can be continuous, like a field theory. And that is basically done, sorry, let me just doing so by a system of Bethe equations. Of course, what I've written here, a very simplified type of the equations, but in general, we can have more complicated systems, but in general, basically, I have a whole system of Bethe equations that allow us to determine the momentum, the physical momentum of my particles in my system by just actually giving the information of the two particle scattering matrix between the particles I and J, or J and K in this case. So once I have these physical momentum, then the energy is just an addition of the energies of each one of the particles, where this E is just a function that is well known for each system. It's the dispersion relation. And it's basically, for example, for the relativistic system, I just have the usual dispersion relation given a mass and a momentum. And in this particular case, which is what we'll use next as well, we can actually redefine the momentum and the energy as dependent on the mass and the rapidity of the particles. So the mass and rapidity. In ADS-5 process 5, each excitation has a different dispersion relation. It's not relativistic anymore. And for example, it is given by this, where this is the coupling, and that's the momentum. So what is the validity of these equations? So the Bethe ansatz can be exact, for example, in many of the discrete cases, but for integrable field theories, actually in general, it will only given a large L. Well, it's valid, but it will only give me the corrections at large L. So both the expression for the energy and the Bethe equations will give me a large N, a large L first approximation. But then what will I have? I'll have corrections. And these corrections are basically coming from quantum phenomena, like the fact that we'll have virtual particles circling my my volume L. So the question is, what are these corrections? So what type of corrections can we expect here? And meaning one of the first approximations that one can do is actually calculated by Lcia. And here we're just assume that we have one single massive state, A, and basically what I will have is now a virtual particle B going along this around the cylinder. So, and I'm assuming that this region has a large volume, sorry, L. So what I can calculate is basically the energy correction coming from this. So the Bethe equations would give me the leading L correction, and now I would have a correction from the fact that I don't have infinite volume but finite volume. And the interesting thing about these corrections is that you can actually calculate the energy correction, but what you need in terms of information is just the infinite volume scattering information. So basically you need the infinite volume S matrix, which is here. And this is, meaning there's different corrections. This is particular to the F term, is just having just a single particle, virtual particle going along the cylinder, but you have other types of corrections as well. This is just indicative in any case. So what we have is meaning here is an exponentially small term, if you can see. So the E here is just the dispersion relation. Oh, sorry, not the dispersion relation, but the energy with respect to the rapidity. And here again, you have the scattering data. So these exponential terms that show up, sorry, the exponential terms that show up here, basically, if the theory is massive, these will always be exponentially small. And the reason is very easy to tell, because what we have is that, sorry, that exponential is minus Lm because of what the shape of the energy is. So basically, these for masses, for m non-zero, this exponential will always be too small. So what we have is that then all these corrections to the infinite volume, large volume will be really small. So there's generalizations of formulas like this. For example, here I was just saying that I had a single physical particle. I could have a multiple physical particle state, of course. I could have more virtual particles going along the cylinder and interacting with themselves as well. And that would give us, you know, extra corrections, more exponentially suppressed corrections as well, and different corrections to the multiple particle state. But in order to actually derive these equations, one thing that we need is a different set of tools, which are called the thermodynamic Bethe ansatz. Again, sorry, I think that this probably is very well known to everyone in this community, but it's just as an introductory of all these formulas also for what's coming afterwards. So what's the thermodynamic Bethe ansatz? Well, it's a method for calculating a ground state or excited state energy of some integrable field theory in finite volume, but it only uses the infinite volume scattering data again. It uses the fact that if you do some double Wick rotation to the partition function, what you have is that the partition function then at imaginary large times is dominated by the ground state energy. And then the large volume corrections can be calculated in some sort of saddle point analysis and will come as exponentially small terms. And actually the results of the thermodynamic Bethe ansatz is a set of nonlinear integral equations for the so-called pseudo energies. So these pseudo energies here are basically in some way the Wick rotated energies, and they're given by the usual part coming from the dispersion relation, the scattering information between, so this is the rapidity of the pseudo particle theta, and the theta i's are the physical rapidities. And what I have here is basically the interaction between these particles. And then I also have a whole set of integrals that would be exponentially suppressed for massive for massive theories. The K is just the interaction kernel. So this is just the interaction kernel. And here again, meaning if you expand this, if you assume that this exponential is very small, and you expand this log, what you get is a whole set of exponentially small terms. So the physical rapidities then, the theta i's that are showing up here are the physical rapidities. And the physical rapidities are then basically solved like a quantization condition by bringing the pseudo energies back into the physical non-Vic rotated kind of plane. And what you find is basically this is the quantization condition of the physical rapidities. And then once again, if you have the physical rapidities and you have your pseudo energies, then the energies given just by the usual sum over the dispersion relation of each one of the particles. But then you also have a whole set of integrals that basically are the contribution from those virtual particles that were going around the cylinder. So these, if you expand it again for massive theories, if you expand it in assuming that is exponentially small, you would get these Lcia type corrections. So again, I did mention at the very beginning that my interest is actually studying examples in ADS-CFT, and the integrability has been quite successful in the ADS-5 process 5 case for anomalous dimensions of gauge operators, semi-classical energies of strings, and typically the Bethe ansatz gives us the leading energy, and again the TBA gives us the wrapping corrections and exponentially small corrections. One thing that was novel when we started studying a different type of ADS-CFT was in the ADS-3 backgrounds. We did have the full S matrix already. We do have the full S matrix. We have a no loop Bethe ansatz, but there's one novel feature compared to the previous cases, which is the fact that we have both massive and massless excitations in our theory. And one can ask, so what are the consequences of including massless excitations in the integrability picture that we have of ADS-CFT? And I just would quickly like to tell you just something that we studied a while ago to try to understand how did we see that there was definitely a difference between just studying, for example, strings in just ADS-3 spaces and in the worldsheet, and also the Bethe ansatz picture and calculating the energy corrections. So for the SU2 circular strings, and I'm talking about circular strings circling in one of the S3s, I can just perturb my solution and try to calculate the energy correction coming from these perturbations. From the worldsheet, we can do this, and we can sum over all the frequency modes of these fluctuations, of the perturbations. And also from the Bethe ansatz point of view, we can do this as well, and we can expand the S matrix at strong coupling. I'm doing the semi-classical strings, so I'm perturbing the S matrix and trying to calculate the correction to the energy of these strings. And what you find is that the two solutions are different.
It might be also just worth saying that now we also have the exact massless TBA as an extra, you know.
Well, I typically do mention it at the end as the conclusions, meaning that there's no, meaning there's more information than just the old loop Bethe ansatz. Indeed, there's we have basically we have information about certain sectors of the theory. We're just missing the coupling between them. Well, actually, more than that, but still.
But so some of our excitation never coincides with the Bethe ansatz. Only through up to exponentially small corrections. Yeah.
Sorry?
The sum of fluctuation energies don't coincide with the Bethe ansatz. It's only exponentially in the length.
No, they don't. Meaning you
yeah,
actually
but even in
find...
ADS-5, I mean, even in ADS-5, they shouldn't coincide.
No, basically you can calculate the. Okay, you can go corrections of you can go to the corrections. Sorry, I heard something.
Someone needs to be muted, probably.
the beta ansatz will give you all of the power law corrections in 1/L. Still, it won't give you the exponential small terms.
Okay.
And the world sheet, you could in principle do some sort of the same thing. So you could have a kind of 1/L matching with the beta ansatz. Here, actually, the beta ansatz will not be enough to give you the 1/L corrections.
So none of them are starting from some power.
None of them will be starting from some power. Sorry, I didn't understand. So they will be. They'll have the. Meaning you. Sorry, tell me. Yes.
No, just you say so. These two expressions do not coincide. They never coincide, right? So what is the precision? What is the difference? Which order in 1/L is it?
It's not even at the leading order, meaning they don't match at all.
Okay.
And as it happens is that's what I'm going to say. That as it happens is that all the wrapping corrections actually show up at exactly the same order. So you need to add them all.
So to be precise, this probably depends on which solution you consider. For folded string, the matching could.
Indeed, meaning how the matching works. There's some solutions where you could actually get a matching, but you wouldn't be able to get. Generally, you wouldn't, because there's no guarantee that the wrapping corrections won't show up at exactly the same order. So basically what I'm trying to say is that let me look back at so the beta ansatz actually is not enough, because these what we used to call exponentially small terms actually are not exponentially small anymore, and they're actually of the same order as the corrections from the beta ansatz. And basically, let me just give you the example of the large volume Lcia corrections. So I had mentioned this, so this is the energy correction coming from just a single particle. But what I want to focus on is on this exponential. This exponential comes with a m0, where m0 is the mass of the virtual particle, and then you have cos theta L. And I want to take the massless limit, m0 goes to 0. And basically, to take a proper massless limit, what we want is variable. So the rapidity stops being, so when we take mass to 0, the rapidity tends to infinity, but the variable that actually is meaningful in the massless limit is the momentum. So we want the momentum to remain finite. And what we need then is not the energy with respect to rapidity, but we need the energy as a function of the momenta. So here in this plot, what I show is the energy is dependent on the momenta for example, a case where the mass of the virtual particle is non-zero. And in that case, meaning that what shows up in that exponential is basically always non-zero, which means that the exponential showing up here will always be suppressed. However, if the mass actually goes to 0, what happens is that around the point where the momentum becomes 0, you have you actually have a region where this exponential will not be exponentially suppressed anymore, and it will contribute exactly at the same order as the beta ansatz. So basically, the conclusion is all wrappings can contribute at the same order. They will contribute to this comparison, and the full TBA, including non-trivial interactions between massive and massless particles, is needed. There is one tiny detail here, which is, massive massless TBAs do exist. Typically, what has been studied is situations where basically, if you study the interaction between these massive and massless sectors, they just decouple, and you can study them separately. But our interest is actually in a situation where this does not happen. So we would like a case where the massive and massless sectors do basically contribute to each other's energy corrections or to the pseudo energies. So what we will do is then we study a double scaling limit of certain homogeneous sine-Gordon models in which some of the particles will become truly massless while keeping the other one massive, and we'll see that there'll be a non-trivial interaction after this double scaling limit.
Could I ask a bit naive question? So why are there massless excitations at all? And say in ADS5 there were no, and ADS4 there were no. Why now?
It's direction. So in case of so in the T4, meaning you have massless excitations, obviously, right? But it's not just that. It's actually if you include certain point-like particles that explore both, like one direction on one of the S3s and the other direction on another one of the S3s, you'll find that actually they're massless.
Mm-hmm.
So the fact that you have these different factors will make it such that you'll have these massless.
So is it true that whenever you have a cassette which contains more than 2 factors, you will get some massless modes because there are only 2 Virasoro constraints to kill?
I would naively say yes, but I actually am not completely certain. But meaning from the cases that I've seen, yes, basically, once you have that to 2 cosets, unless, again, if you had a T4 just generally, you'll have massless excitations by default, of course. But also, meaning that here, you would also have a massless excitation just because you have something on the S3 and something on the T4. So what I've seen is that is true. I don't know if that's a theorem, though. I would have said so. Because, yeah, the Virasoro constraint isn't enough, meaning there's...
I ask a question. Probably your situation with ADS3, etc., is the one with purely massless spectrum plus purely massive spectrum. There is no like continuous spectrum going to 0, gapless. No,
yeah,
because it's also, it does exist in integrable world, like the model we studied with Kostya and Zhenya, principal chiral field at infinite n. It's curious how the TBA works there, or at least Lcia corrections in this situation.
So, but you can tune meaning you can tune masses, or you just have a whole range.
At the large limit, the principal chiral field simply has continuous spectrum of masses.
Okay.
There are more and more masses, and finally they are just they form continuous spectrum. So it's another curious situation with massless spectrum.
And massive.
Mm-hmm.
But they already know TBA, so it's not a problem, right? So you know exact equation. So whether they're massless or not, it's already irrelevant. I mean, if TBA works, it works. It doesn't rely on masses.
But it may have
TBA needs masses.
The TBA in this case. Anyway.
So just a curious addition, maybe that is a little simpler than the TBA. If you have mixed fluxes, so if you have some NS flux, or if you instead want to phrase it differently, if you're in the Vezumino-Witten theory with non-zero modulus, Ramon-Ramon modulus turned on, then the mass is actually not a constant, but is of the form m plus kp, where k is the Vezumino-Witten level. So as the effective mass changes as you vary the momentum as well.
And you probably reach this situation when it's gapless, the spectrum. No?
So in that case, indeed, yeah, the sort of there's even the sort of massive modes have a point in some momentum space where they behave like massless guys.
Mm-hmm.
But that happens purely in the Vezumino-Witten theory. As soon as you turn on any amount of Ramon-Ramon modulus, then it becomes genuinely gapped.
Mm. Okay.
Another simple question. So you say you need TBA from the very beginning, but TBA itself is based on the mirror theory. So if you take mirror theory of infinite length, I still say you need always TBA corrections from the very beginning. How it breaks the loop argument? So mirror theory, to derive TBA, you need mirror theory where you can use asymptotic beta ansatz. But just explain to us you cannot use asymptotic beta ansatz any time. So how you actually would proceed to derive TBA then?
Well, you can imagine there is some massive deformation, right? And then derive there and then remove the deformation. but never actually introduced deformation in practice. I know.
So one thing that I'd like to say is that so I will go to the homogeneous sine-Gordon models. I will not talk about Lagrangian formulation. Apologies for that. So if you look at, this is the original paper where the first Lagrangian formulation for these models showed up. There's also a paper by Miramontes Park, I don't think it's Hollywood, sorry, which is also 96, which then develops a bit more. I forgot to add this here. And also, in terms of the TBA, many you have the paper by Castro Alvaredo and several other authors as well, of course, in 99, which does the TBA for the homogeneous sine-Gordon models, in particular the ones that I've been mentioning today. And also, they actually analyze the full massless, completely massless limit of these cases, and actually analyze the central charges that they get from a possible CFT, which was another question that we were talking about last week. Sorry, I did not have the time to actually read it properly and actually put enough information on slides, but the information is definitely here. So in terms of today's models, what we'll do is focus on the SU3K homogeneous sine-Gordon models, which actually have 3 adjustable parameters. And basically what they have is 2 masses of particles and also a rapidity offset. And these are the elements that we'll use on our double scaling limit. Of course, we'll keep one of the masses to be non-zero. We'll take one of the other mass to 0, but in such a way that we'll use the rapidity offset to make the interactions still finite. So today, what we'll do is the SU32 model, where we have 2 types of particles, one of each mass. So one of mass M1, one of mass M2. And what we'll see is that we will have, when we do the massless limit, we'll have a non-trivial massive massless interaction, but it will not be enough for what we would think happens in ADS-CFT, because it's actually a trivial massless. But this is the one I will be focusing more, because it's just an introduction to the limits that I'm going to do. But in any case, this is what we can expect. And then I will go to a slightly more complicated model, which is the SU33. Now I have 4 types, of particles. So basically 2 of M1 and 2 of M2. And now I will have a full non-trivial interactions when I take the massless limit, and the full TBA then, meaning if I have a physical state of massive particles, which is what I'd be interested in, I'll find that the full TBA is actually needed to describe the energy corrections for those massive interactions. So these are the...
Could you give us a little bit of a flavor of what the Lagrangian looks like for these theories? Doesn't have to be precise, but just to get a feeling for it.
It's a deformation of the Witten Lagrangian. Sorry, it's some particular deformation
of SU3 Witten.
I think so, but
So it's not in the style of affine Toda field theory.
It's not?
It's not that similar to affine Toda.
I don't think
Probably.
it's equivalent to affine Toda. It's some generalization of, yeah, again, it's some generalization of the complex sine-Gordon.
I see, okay.
So it's not quite the same, but it's again, it's some deformation.
Is it just SU3 Vesumino Witten with some funny mass term added or something like that? Or?
Honestly, I don't remember how the mass term is. It's a weird mass term, but I think so. It's basically just the action of the Vesumino. SU3, meaning the SU3K specifically, I think it's the SU3 Vesumino, but then you have a whole massive sector, and but I don't have it open. Yeah.
Oh, so there are more fields than just Vesumino fields? Or?
I think so. Wait. I mean, that's a good question, which I don't know the answer. I could, just a second.
Yeah, it's okay. I mean, don't worry if it's breaking the flow. No problem.
Well, my biggest problem is that somehow my video sharing is paused. What? Resume share. Now, I guess I can't do anything. I'm sorry, I can't even open my computer.
No,
I just tried
worry,
to, because I have the papers right here, but the screen doesn't.
Let's move on. If you can send the answer in the chat during the coffee break.
Okay, so then, meaning as soon as I finish it, meaning I'll send it to you, I promise. This is as much time I had this week. I really wanted to actually try and write up, but I didn't.
Yeah, let's move on.
So now, okay, so let's continue. So this is the two things that I will be looking at, but I will be first focusing on this particular case because it's definitely a much simpler model. So how is the setup? So I have the particles, like I said, it's two particles, I equals 1, 2 of mass mi. I have diagonal scattering, so, and basically what I'll have, I'm saying, and what I have then, it's the S matrix, which is given by S. So what I'm interested in general is S of theta I minus theta j, and where S of theta is -1. So this is a minus th of 1/2 of theta. And from here you can see that the particles of the same mass scatter trivially, and that particles of different mass have some non-trivial scattering. And again, you see here the introduction of this rapidity offset, which is this parameter sigma, which is adjustable in the theory. So what we will want to study is I do apologize in advance if a 4-year-old just bursts through the door, but I just heard him, but I don't know. I think they might be going. So I'll be interested in looking at the excited state TBA, which was done by 96. By the way, sorry, I didn't write here that, of course, theta is the rapidity. And basically, I'll use most of the cases, unless I forget, I'll use theta for the rapidity of the massive particle. I'll use phi for the rapidity of the massless particle. Of course, at the moment, it's M1 and M2, so this doesn't yet make sense. And I'll use a theta hat for the physical rapidities. So what I'm interested in is studying the excited state TBA, but where my physical state will be composed of excitations, all of mass m1. So I'll have the physical states, all of the mass, but I'll keep the mass finite. And what we'll want to do is the next, we want to somehow take m2 to 0. So what is the TBA? I'm not going to write this. It's the same idea as the TBAs before that I've mentioned. So we have two pseudo energies.
So can you comment how is your description related to representation theory of SU3-2? I mean, you say it's diagonal scattering, so I'm not sure I understand it.
So, sorry, it's diagonal scattering in the sense that it's meaning the particles go 1, 2 to 1, 2, and so it's just so I have two particles, and it's just meaning there's a
no. So are they reps of your symmetry group, or I mean?
I think Dima is asking where are the auxiliary particles, like auxiliary beta roots.
Or flavors, right? I mean, where are flavors?
It's not a nested beta ansatz. Not that I.
No, but you say you have SU3. It's based on SU3 2, like level 2. So what I mean, what type of representation of particles of this group?
Oh, that's a good question. Which I don't remember. Sorry, I really don't remember. SU3-2, that's.
Yeah, I think we can also move on.
Sorry, I don't remember. I just took it honestly for this. I just took the actual meaning. I took the known TBA with the known S matrix, and I did not check.
But Dima, what's the problem? So you have two particles. One you can say, so you have a strip, right? And there are two particles. That's perfectly.
No, I understand. I know. I understand like the description, right? I just asking there is for some name given, and I cannot link to the name, but we can move on. Yeah.
So, okay, for the pseudo energies, so I have obviously two pseudo energies. They're, meaning one thing is that, so now what we would have to focus on is like the integral parts of these pseudo energies. So the pseudo energies are given by the same as before. One thing is that, so this phi I just comes from the fact that the massive excitations are just trivial, acting with each other. And we only have in the physical state, we only have massive excitations, sorry, M1 excitations. And here, of course, it's the interaction between M1 and M2. And again, we have the interaction kernel, we have the exponential terms. The physical rapidities are just the solutions of the pseudo energy E1 in the physical strip equal to the quantization condition with the mode numbers, and then the energy of the physical state again. And I just want to highlight the three integrations. And why do I want to highlight the three integrations? Well, because if I drop all of these integrals, what I have is just the beta ansatz equations, of course. And again, for the massive particles, meaning if L1 and L2, if M1 and M2 are massive, as it happens, sorry, so dropping the integrals, so if I have the massive, I didn't want that. Particles, what I have is that the Li's of theta are going to be of order exponential of minus MIL, so exponentially small. So this gives you, so dropping all of the integrals here means that I will just get the energy up to polynomial accuracy, basically in L. So here means so beyond this, what happens? So at this, okay, this is what I wanted to do, say here in massive particles in large volume L, sorry. So beyond this, what I have is corrections from the integrals. So and in particular, what I have is that the energy, I can say that it's the energy of the Bethe ansatz that I could calculate just with the Bethe ansatz. And then I'm going to write this like that. So this here, I'll say delta E Q, and here it's the delta E integration. So as compared to the Bethe, what do I mean by this? As compared to the Bethe ansatz, I actually have two types of corrections. And the two types of corrections come from the fact that the physical, when I calculate the physical rapidities, and I include these integrals here, basically the theta k's get corrected. And that is what I meant by this delta EQ of the quantization condition. And also, of course, I also have the contribution from this integral, which is from directly from the virtual particles themselves as well, which gets me this contribution, which is the delta E int. And what do we want to do now? Yep. So what we want to do now is take the M2 to 0. But when I mean take the massless limit, I mean that actually I want the contribution M2L to be 0, meaning I will really want M2 to go truly to 0. So, and of course, I want to take L to infinity. So somehow I want to really cancel the M2 completely away from my TBA. And the question is then, what happens to the integrals that I've mentioned here? So to these integrals with the L2 and the L1. And for the contribution of the energy, what happens to them? So, as I mentioned at the beginning, taking the massless limit, what we expect is that the momentum P equals M2 SH of theta to remain finite when we take M2 to 0. So what we'll end up doing is actually taking the rapidity to be very large, and while M2 is going to 0, such that the momentum, which is my new meaningful variable, to become very large. So basically, sorry, and here I actually, because it's now the rapidity phi, so what I want is phi to grow large, and M2 to go to 0, and P finite. So again, so if I want M2L to go to 0, basically when L goes to 0, what happens to the L1? So the contribution coming from the L1. This contribution will still have an exponential of -1 L, and that basically is what you can see here as this bump here. Basically, yeah, I wrote on top of it, and now we can't see the difference. So there's a small difference between the vacuum solution and the red line, and basically it's only at the very peak that is different. And this contribution basically will because this here, when L goes large, basically will drop to 0. On the other hand, the L2 will become of order 1. And it will be almost like the vacuum, except at the region where phi is very large. So basically, this is the larger the phi, the larger L, the more this bump will actually go to infinity. And we want to somehow zoom on this regime and ask for a double scaling limit such that I can actually stay on this regime always in my TBA. So as it happens, what happens is that then so once I actually, so this is the type of integrals that I'll have, and what will happen is that once I change variables, I know that this will be of some order of this type, which is actually of order 1 over L, which will contribute now to the leading energy corrections as well. But in the TBA, if we naively just take the massless limit to 0, basically the massless, the massive massless S matrix becomes constant. So we don't want to do that. We want to somehow do a double scaling limit such that the S matrix actually remains non-trivial. And this is the double scaling limit that we'll do. What we'll do is take M2 to 0, sigma to infinity, which was the, sorry, let me just perhaps. So here, for example, in the Kij, if you look at the interaction kernel, the theta came with an offset of sigma. In the S matrix, the theta came also with an offset of sigma. And what we want is now use that so that we take M2 to 0 and sigma to infinity such that there's a relationship between them. So sigma plus log M2 over 2 is finite. And that actually, if we do this, actually, if we change phi, so P was basically for phi very large, so we take the rapidity to be large. So this is just M2 over 2 e to the phi. Basically, as approximation, the sinh phi is going to be e to the phi. And so we can do this change it in the S matrix. And what we find is that basically we can go from phi to P, and the new S matrix will become non-trivial for momentum greater than 0, and basically trivial for momentum less than 0. As it happens, this particular choice of this double scaling limit, where we chose that sigma is positive, will keep a non-trivial interaction with the right-moving massless particles only. The left-moving massless particles still completely decoupled. If we chose a different sign for the sigma, we would get the other ones. One thing that so this is the right-moving particles. And another thing is that, so the S12, as it happens, will be similar, very similar. And all the others are trivial because they were already trivial before. They're always already a constant. So the pseudo energies now up to, and now when I write the TBAs, I'm always going to write up to exponentially small terms. The exponential small terms come from the fact that mass M1 is not 0. It's different from 0. So, and the pseudo energies are just given by the same thing as before. The E1 is still going to be given by the same thing, but now it has a contribution coming from the E2, which is not going to be exponentially small anymore. So the E2 of P goes as L mod P, is the integral that I had mentioned before here. So it was that integral that I was mentioning here. And it will still have the interaction matrix included in it because it's non-trivial. So the physical rapidities is also the same quantization condition for the theta case coming from the E1 because all the physical particles are of mass M1. And then the energy is again given by the corrections to the physical rapidities and then the integration part. And actually, I've forgotten to write something because an interesting thing is that actually, if we're careful about including the left moving and the right moving, we actually get a contribution that comes from momentum less than 0, which is just a constant number. So let me just write to you what the results are. So here I have the delta E in, so the part of the integration. I also have, of course, the corrections to the theta case. And these two, so the theta 1, meaning now I'm assuming one physical particle only. And what I have is like, I will have the theta 1 that you can calculate the 1/L corrections for the physical rapidity. And then you can plug it back into the delta E int to calculate the S matrix. And what you find is, again, that constant part that comes from the momentum less than 0, and then the part that has the momentum greater than 0. And this can be done actually exactly order by order in 1/L, and you can calculate all the contributions. So one thing that I would like to say is that, so obviously we cannot expand the integral in exponentially small terms. Oops, sorry. In exponentially small terms. Why? Because this mass is now 0. So, or actually, sorry. In this case, what I would have is L mod P. So I cannot expand now in wrapping number, which is this exponential. Why? Because all wrappings are of order 1/L. So this is now not a good expansion parameter. But actually, there is still an expansion parameter. And the expansion parameter is, we can expand in 1/L by keeping the momentum small. So by keeping YPL fixed. So you keep in the integrand y is a new variable p, which is PL, and you still expand in 1/L, and you can obtain all the corrections in 1/L.
May I ask something? You have here only the first Lcia correction, yes? Because you just inserted the S matrix. But there are next terms. Why do you think they are not mixed in powers of 1/L?
No, this is not the first Lcia correction. This is the full TBA.
Wait, you have here
I have the log of 1 plus e to the minus epsilon 2 of P. So this is 1 plus.
Which you can fix, but usually in TBA you cannot define it. But you probably play with L. It's big L.
In this case, no. The epsilon 2 is actually very simple. It's just this. Up to exponential small terms. Sorry.
Yeah, that's what I say. But
no, but the exponential small terms come from the fact that mass m1 is non-zero. So it would be exponential of m1L. In terms of the massless scattering, which is going to be of contributions 1/L, 1/L squared, 1/L cubed.
So it's exact
all
solution.
of them.
It's not just first correction, but it's exact solution in all orders except exponential.
Yes.
And that's why you control the 1/L powers. Okay. Mm-hmm.
So basically, this is exactly what I've done to actually calculate that expansion. So another thing is, of course, like corrections to theta k. As I mentioned, the TBA also come from the quantization condition of the TBA. And it will contribute, actually, as it happens, they show up at order 1/L squared for the TBA. So they would show up, that's what I'm writing here with the C1. The C1 is the correction that comes from the fact that the theta 1 is corrected from the TBA as well, from these integrals. And now just one other thing. So this is what I meant. So delta, what I wrote as before as delta Q was going to be of order 1/L to the cube. Sorry. Yeah, so the delta cube comes with 1/L, so it will be over 1/L to the cube, sorry. Yes. So summarizing, we did a double scaling limit. And what we got is that the massless and the massless, oops, I can't write massless anymore, sorry. So the massless virtual particles contribute to the energy of the physical massive space. So contribute to the spectrum of energies of the massive states. But as I mentioned before, when here, I don't have any contributions between massless excitations. So that is definitely missing from this example because it's too simple. And just to give you an idea of how much more complicated the next example is, which actually has all of this information. So we go to the SU33 homogeneous sine-Gordon. Now we have 2 particles of each mass. So AB labels the particles, IJ labels the mass. The S matrix is from a particle A and a particle B, and of masses I and J. And it's given by this. So there's if the masses are the same, you have a non-trivial interaction. If the masses are different, again, also another non-trivial interaction. Just notice that the rapidity offset, which is the sigma ij, only shows up in the cases where the masses are different. And basically, this is the definition of the elements in the S matrix. So what do we want to now? We want to find, well, not find, we want to write a TBA, but and one thing that I want is that the excited state, so the physical state, is just of type of excitations A equals I equals 1. So my physical state is going to be a single type of particles, A equals I equals 1, and then I will try to, so it will be mass M1, and then I will try to actually do the massless limit and see what remains. So yet again, what is the TBA? The TBA is 4 pseudo energies now for each of the particles and each of the mass. It's given by the usual thing. So the fact that I have here the 1 is because I'm assuming that the physical state is of A equals 1 and I equals 1. I still have my integrals, and then the physical rapidities are given by the E11 exactly for the same reason that I've mentioned, and the energy will be given by the same thing. And then what we want to know is what happens to these integrals. So it's the same idea, it's just that now we have 4 particles instead of 2. 2 of them will be massless, 2 of them will be massive. So there's some simplifications in this model, they're well known. So I'm first taking the mass M1 to 1. I will drop all exponentially small terms that are exponential of minus M1L. And so again, the physical particles, as I mentioned, are this type. And also the pseudo energies, actually, they're 4, but they're complex conjugates of each other. So the E22 is complex conjugate of the E12, and the E11 is complex conjugate of the E21. So I actually only have 2 that I need to study. And they're basically, I've rewritten them like this. So this one will give me the physical rapidities. This one will be what shows up in the non-trivial integrals that I need to calculate. So again, these are the same thing, the energy. So again, it's L12 plus the complex conjugate. So how can I use now how can I solve this now? What I can do is, I can either do this numerically, take the mass M2 very small, the L very large. Be careful that I really want M2 times L to be still small in the numerical analysis, and see what I obtain. And I also want to actually rewrite this TBA such that I actually get rid completely of the mass M2 and see what is left. If I do that, so again, what happens? If I take M2 to 0, sigma to infinity, keeping this sigma not finite, this relation between sigma and M2, the S matrix, well, the relevant element that shows up in the TBA that I'm solving is given by, again, just the right movers. The left movers are basically have a constant S matrix. The pseudo energies now can be written in terms of the momentum, as this is the same term that we were finding before. But now I don't only have the S matrix, but I also have a whole integration that comes with it, which it corresponds to the interaction between massless particles. The quantization condition comes from the E11, and it can be written exactly as well, and the energy. And now, what do I need to do to solve this? Sorry, and I'm almost done. It's like for large L, what I'll do is, again, expand in 1 over L, keeping while the new variable y, p times L fixed. And I can do this by taking, sorry, I'm not sure if I haven't written this. No, I didn't. So basically what that means that I can write E of p as an f naught of y plus 1 over L f1 of y plus 1 over L squared f2 of y. And also, meaning for one physical particle, I can also correct my physical rapidity. And the idea is that actually what I need to find is these functions f0, f1, and f2. And one question is this actually doing this expansion in 1 over L, keeping the y, p times L fixed, does it work? And one of the things that we want to do is compare to the numerical calculation of the TBA to make sure that actually this is appropriate. And doing that.
Should we have a break or we go to the end?
So I'm sorry, I don't know, this is my last slide.
All right, okay, let's then continue.
If, in case you, so I can actually do that, and what I obtain is like I can find the corrections that coming from the quantization condition, the corrections to the energy that come from the integrals, and you can see the 1 over L correction to the integrals come just from the f0, the 1 over L squared comes from the f1, and then on and then on. And this is comparison with the numerical solution, including just the 1 over L term in the energy, the 1 over L squared, and the 1 over L cubed. And what you find is that the error decreases with each order. There is an issue here when we include the 1 over L to the cubed, is that at some point in M2 times L, we actually lose some accuracy and we get a problem right there. But this is a numerical problem and it's not an actual accuracy problem. So what are the conclusions? Basically, that the spectrum of massive excitations.
Sorry, from this diagram, how do I see that it gets better? I just don't understand.
So this is the absolute, this is the energy coming from just including this term minus the energy of the of the numerical calculation of the TBA.
I mean,
when I took
it becomes like 10 to minus 4 as compared to like 10 to minus 2.
Yes, and the higher, we have to say that the higher the L, the better the accuracy, because it's still a large
right.
L.
So at L100, we see we gain like roughly two orders indeed, right, each time.
Yep.
Okay.
So the spectrum of massive excitations depends on the massless sector, and it definitely contributes to it, including, so another thing, and this is the main thing, including self interactions of massless sector. So another thing is that either left or right moving massless particles contribute. So we can't make both of them contribute. I think we need a more complicated theory to actually have both of them contribute. They're only the left or the massive, or the only left or the right will be coupled to the massive states. And the last one is that, again, as before, this cannot be used. So the wrapping order cannot be used as expansion parameter. 1/L series can be obtained by basically changing the variables to this, keeping the L times P fixed, which is small momentum. Okay, what can we say towards ADS-CFT? Well, we would like to incorporate the massless modes in the full massive massless TBA, hopefully actually using the recent results where the full massless TBA of the ADS3 is already known, and maybe, I don't know, adding some deformation and being able to play around with masses. I have no idea how one would be able to actually use all of these results into the full ADS3 TBA. But one thing that we can probably do is actually learn how a TBA would look like that would include massless and massive particles at the same time. So just as I mentioned, if you want, now I can stop. This is that is all, meaning if you want to see the full TBA, it's written now here, Bogdan. So it's 3 pages of it.
Well, as you know, I need to leave in 3 minutes, but,
but yeah, but
I will not.
I've written it here, so then in 3 seconds I'll show you the full thing. There we go. Sorry. But yeah, so I've written it here. I can give it to you, but with the full, with all the epsilons, so, and the S matrix. So this was just a question that I was expected that Bogdan would ask again. Yeah, but thank you. And sorry for taking a bit longer than I thought again.
Well, you are probably the shortest talk in the history of this series. So let's thank, it's Andreas' work actually. Andrea.
Hi, yeah, thanks Ines. Yeah, thank you very much for the nice talk. Are there other questions?
Yeah, well, let's thank first, right? Unmute.
Yeah, sorry. But last week it didn't work. Nobody clapped.
Yeah, actually, I have a question. So you have this power-like corrections. So to which extent these coefficients in front of powers depend on particular configuration in the massive sector? Because you can have different solutions in the massive sector, right?
Yeah, they will, meaning all of this, of course, will depend because when you write here, the pseudo energy, if you can see here, will depend on the S matrix with the full massive physical excitations, which and this actually changes. Meaning even in the simplest example. Sorry, give me a second. Just to, when I've written here, this TH of L log P minus theta K. So of course, this will change how each one of these coefficients show. And this is the S matrix, and these are all the theta K. So if you have a multi-particle state, you'll have a whole set of theta Ks, usually with some relation between them, especially if it's, you know, a long string.
So C1, you can write probably some closed expression for C1 in terms of the beta roots of the massive sector, right?
Yeah, well, for this particular case, you can find them exactly. They're just.
So just my question, is it given in terms of the S matrix? So what is there some universal description of the C1 in terms of S matrix and beta roots? So you're correct in beta ansatz equation, and I just want to know whether there is prediction of what you have to add.
So there is a prediction in the sense that we know what type of beta roots we want. So, and again, for example, if you're doing a circular string, you know how all the thetas are related with the x plus xi plus minus related to the next.
Oh, yeah, but that's already making a test kind of. I mean, from your consideration, what?
From my consideration, this C1, meaning what I'm assuming is that I have a whole theta case. They're all of order 1 over L. That's definitely an assumption. And with that, that's enough to actually solve it. Of course, if you have more than one particle, it starts becoming a lot more complicated to solve exactly for C1 and C2, just because.
Let's say for circular string, theta k's are not of order of 1 over L, right? They're rather of order of L, not of 1 over L.
No, so if you
look at the classical solution, like circular string or folded string, normally the rapidities are large.
It might be after some rescalings, because when you're solving for when you're looking at just
well, normally rescaling wouldn't depend on the length of the chain, because length is something.
So if you ignore this part and you have just the E1 equals M1L cos theta, right? So, or basically, if you actually, when you're solving for this, what you have is M1L sinh theta. And M1L sinh theta, if you want this to be of order 1, it's better that the theta is, if you have just 1, is of order 1 over L.
Yes.
And again, if you start adding more thetas, then you're allowed a bigger variety of options in terms of solutions, of course. So I would have said that without knowing exactly what we're describing, meaning you can add as many particles as you want, but whether they're going to be meaningful.
So my question is, can you fix this mismatch for the classical solution, which you mentioned in the beginning, with making some guess of what the interaction between massless and massless is?
So we've tried that. When we did the Lcia, meaning we did these Lcia corrections, and we tried to see what taking the massless limit of that would look like, which basically means that you have some shape of the interaction kernel there. But again, we did not. We only did that, and we did not consider. I can't remember whether we considered the actual corrections to the physical momenta. We just wanted to show that that integral actually contributed to the same order, but I don't think we included the corrections of the physical momenta. So actually, I don't know. Because I guess the corrections to the physical momenta would give us information about this particular integral, while what we calculated was this integral alone. So, or we didn't think, okay, we did not calculate this integral alone. We calculated what we thought were the reasonable expectations for a multi-particle Lcia corrections of some sort. Anyways, that's as far as I know what could be done. So, sorry, long story short, I don't know the answer. I don't know if one could try and analyze the corrections to the theta case in order to find the TBA, basically, the interaction kernel or something.
Thank you. Any other questions?
I have a question.
Yes, please.
Starting from massless case, can you consider finite mass corrections?
Yes, is the short answer. I'm pretty sure you can. I think some people are working exactly on that option.
Do you know how does it look like?
I think that's, or wait, I thought that was what they were trying to do. They were trying to do, yeah, like corrections to try and see if they could generate the TBA through something like that. But again, I don't know. I haven't seen it. I just know that was one approach there that some people were trying.
Any other questions?
Sorry, once again, about, it's the same question which I asked. Maybe I didn't understand quite the answer. So you have non-interacting particles. Do you have non-interacting massless particles? Because probably it's the only way you can solve the TBA, at least for massless part.
You don't, you have interacting. So for the first case, you had non-interacting massless particles.
Yeah, that's why you have explicit expression.
Exactly. Here we don't. So here, basically, what ends up that we have, what we end up having. Sorry, give me a second. If I can look. So, I know this is, sorry, I'm just. So when you see this, when I wrote here that I was expanding this pseudo energy in terms of this F0 of y, F1 of y, F2 of y, as it happens, meaning solving for these F0, F1, F2 is like solving a nonlinear integral equation for each one of them. So you're also doing a numerical solution for these functions. So you can't solve them exactly.
Yeah, but when you write in the next transparency the exact right-hand side for the energy, this means that you simply use the Fermi distribution for massless particles, and that's it. Yes.
No. So here I'm just expanding. I said.
Maybe I better understand the previous transparency where you have
so
even the previous one. When you have the energy, even the previous one. I mean, we discussed it once.
So, but here again, yeah. there was definitely no self-interaction. So yeah, here,
that's why you have.
Here, there's no self-interactions. You can actually do the integral exactly.
In the next transparencies, of course, you take already into account this interaction. Yes. Those are interacting massless particles. Yes.
Yes. Here there are.
Yes. Otherwise, of course, there is no way to write it that explicitly, because you have many wrappings and they interact. They have S matrix.
Yeah. So again, it's solving. The only difference is that, meaning first that what we did, I guess, is just, sorry, let me just find the, when I write this corrections to the energy, I actually just change the variable such that I still do an expansion in 1 over L. I keep this variable y that I'm now integrating in as L fixed, and you can have this 1 over L expansion where the integrals themselves don't depend on L. But to calculate this F0, meaning it's really like almost like having a TB an equation like for the pseudo energies, but now for the F0s, for the Fis, and you still need to solve them, and because they're self-interacting, you have to solve all of them together numerically. Yeah, so there's no explicit formula to calculate the F0s.
Sure. I was afraid that you solved the TBA.
No. Yeah, that's why I said that. So the reason why we didn't just do the SU32 homogeneous sine-Gordon is because in that case there was no massless interactions. So it was too simple in that sense. While here it's a full massless. You have full massless interactions as well.
Good, thanks.
And any last maybe question?
So no more questions.
Okay, let's thank again.
Thank you.
And so Andrea, could you tell us about next time?
Yeah, so next time we have Tamas, and I see that he is here. So maybe, Tamas, do you want to say something about your seminar?
Hello. Next week I will talk about integrable boundary states and integrable overlaps, and the application at ADS-CFT.
Okay.
Thanks. Great. Okay.
Thank you.
Okay. Thank you, everybody. Thanks, Ines.
So next week is it the same time as today, or what's the plan?
Yeah, we thought maybe to keep it at the same time as today, if it's okay with everybody.
If there are no other seminars at the same time, we will probably keep it on Thursday at 2.
Yeah, I think we are fine next week.
Okay, see everyone next week. Bye.
Thank you.
Thank you.
Thank you.
Thank you.